Alright, another draft physics video presentation. Should have warmed the voice up or something. La 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 and such. Anyway, before I, commence the symphony. I found another one of these Brian Greene World Science Festival videos, and it's just so bad, and this is the newer version, and it's just so bad that, this explains why physics is junk, is because it's just storytelling. It has nothing, then they just want the story to be interesting, more interesting, I don't know. I mean, obviously, just being alive and having physics, a physical universe is already pretty interesting. But, of course, they have to make it into some sort of magical place with magical events, unknown things to just keep everything uncertain, because that's somehow fun. It's, it's roller coasters versus why bother doing that? I mean, I never made any. What? why would I get on that? What, you think I'm stupid? Yeah, so I mean, the world has always been crazy, and it's just demonstrating that it's full of crazy people. I mean, the lunatics are running the asylum. Sad to say.
What drove the initial move into quantum physics?
I suppose more volume might be required. There's always something. I have to go find the right video, and then I have to increase the volume a little bit. Probably too loud now, but whatever. Don't want to cast any inappropriate aspersions or any of that kind of crap, but these people are weird. That's all. They're all weird. Sorry. Anyway, you could use other words for weird, but they're talking weird.
David?
I think it was really just pushing really hard at classical mechanics.
It's like a cartoon character. I think I have it sped up a little bit, but it's not exactly that much to make this difference.
As it went down into the scale of atoms and the structure of atoms, and just finding that structure snapped and broke. That trying to use classical mechanics to understand how hot things got, or how electrons went round atoms without collapsing into the nucleus. In all those places we had a series of hints that...
So that's the real key word, right? Hints. There's a tiny number of experiments that give you some kind of result that doesn't seem, doesn't fit. And so... And in lots of these things, I mean, throughout history, they found out the little variable they weren't accounting for. A building fell down and they figured out, oh yeah, well, you didn't account for the fact that, the substructure of the soil was this or that. So there was some variable they just hadn't accounted for. And that was like what we had learned over time, is that there was little variables. It's like, you can make the argument about... evolution. It had this little flaw in it, like, well, why aren't there any of these missing link fossils? Why are all the missing links missing, all the transitional fossils? There seems to be so few of them. But you had to just understand that the variable is that most of the innovating wasn't happening in giant populations. It had to happen in small populations, because a giant population will just genetically dilute any aberrant. So the aberrants don't have much chance to thrive in a big group of genetic diversity. And, that's just one of the obvious reasons. So obviously there was a lot less transitionals existed than the successfuls, the dominant ones. The aberrants were rare in actual physical population, and so that's why there's this little incontinuity in the fossils move, they're bunched. There's a non-proportional representation. But it's explainable with a simple variable. You don't need to bring in the hands of God.
Something was amiss in our classical physics.
Yes.
And it took guess, most of 30 years for those hints to coalesce into a coherent theory.
You say it's coherent, so that's the word, right? So I'd argue that it's nothing coherent about it at all. It doesn't make any sense. You ended up with a whole different physical universe for the big universe in terms of, Einstein's relativity mush. And then you have this quantum mechanics stuff, whole different thing with virtual photons and force carriers, silly talk. The two are incompatible, and they're both have plenty of incoherence. They're incoherent with each other, which is really bad, and then they're individually have all kinds of coherency issues. So as answers, they're not very good.
But that coherent theory then became not really just a single physical theory, a language for writing physical theories, be it theories of particles or fields, maybe something in gravity, and that language was more or less sort of solid by, I guess, about 1930.
Yep.
Right. So, yes, there was only a small group of people called physicists back then, and a small group of physicists talked about it and decided what the truth was. And I'd argue that it wasn't a very good map they drew. They didn't have enough information, and they jumped the evidence. And that's probably the simple story. And it was the leader of the pack was, unfortunately, there are people with sort of perspective agendas, in the sense that they were etherists and and religious even.
And it's actually quite remarkable that it only took that number of years to develop a radically new way of thinking about things. And Richard Feynman, who is of course a hero of all of us, also known to the public.
So, a hero, so anyway, yeah, so this is the famous words, right? Oh yeah, well, this experiment is the cornerstone of all this nonsense. So because of one experiment that does something a little weird, let's all jump on the God bandwagon. God plays dice with the universe.
Famously said that there was one experiment. We could go through the whole history of everything that you described with the ultraviolet catastrophe and photoelectric.
So that's way over-described, this catastrophe, which basically would only be a catastrophe if you thought it was possible to create infinite energy. So, if you already kind of figured out that there's only a certain finite amount of stuff in the universe that couldn't create an infinite amount of anything, then maybe you'd figure out that, oh yeah, that's kind of silly. So no catastrophe. Sort of. That it's harder to make harder things, it's harder to make, to consolidate something. There's a finite point. It's like going from gas to solid. Why would you have the expectation that you can go double solid and triple solid and quadruple solid? You'd have an expectation that there's limitations.
Effect and all these beautiful experiments, but the double slit experiment, luckily for us, in having a relatively brief conversation, allows us to get to the heart of this new idea, where it came from. This actually is the paper on...
So this is some paper, investigating reported paper was being, electrons by a crystal, blah, 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 blah. So this was some electron two-slit experiment, which, again, I've argued there's no practical way to confine electrons. You can't create anything like the same circumstance that you're creating for light with electrons. Light is, as I've pointed out, its polarization defines it, and its polarization means it's very large. So let me just describe again. For those who haven't been paying attention, a photon could be understood as traveling through space like a rectangle. The quanta aren't perfectly lined up, so they occupy some space in this direction. They clearly have a direction this way in time, that is, they have a length, and but they don't have any width. And so like a little piece of paper, they can all fly through space, different angles, different polarizations, but they're big, very big, thousands of atoms worth of polarization, where an electron is, that. Very hard to make two slits that would be proportional to the size of an electron.
In some sense, the double slit experiment, the first version, Davison and Germer. And I'll draw your attention to one thing. See the word accident? Yeah, I see that up there. I hope it's big enough for you to see in the audience. And this is just a footnote, but I don't know if anyone was at the program with Alan Alda and Tina Fey last night, where Alan was describing how he bemoaned the fact that in the old days, people would actually describe the blind alleys that they went down in a scientific paper. But as science progressed, we were kind of taught, no, don't ever say what went wrong. Only talk about what went right. But
Well, the whole idea that you're quote mining experiments and you know, presenting them in a certain form, you know, to say here, this, you know, is part of the cheat. And it's part of the reason why you draw these conclusions, is because you really don't take it and look at it for what it really is saying. And this is a perfect example in the sense that they say the word two-slit experiment and then they draw the single-slit pattern. They never deal with the fact that the two-slit pattern is a pattern that has two patterns in it. So it's not even part of the analysis. I mean, it's such a cheat of the truth, because they have no explanation for these things.
here's an old paper, and indeed this experiment...
Well, let me just put it this way. Their theory doesn't explain the results at all. So they're saying that they're using their best judgment to describe the phenomenon, but they've taken the reality out of it, and then saying their description is perfectly adequate. So it's like shaving all the fur off a bear or something, and doing something, you know, putting a silly hat on it, and then trying to sell it as a, you know, somebody's brother.
emerged from an accident in the laboratory at Bell Labs. They were doing a version of this experiment. They turned the intensity up too high. Some glass tube shattered, and when they redid the experiment, unwittingly, they had changed the experiment to something that was actually far more interesting than the experiment that they were initially carrying out. So just to talk about what this experiment is.
So it didn't, you know, didn't give us any details on that one. So not very interesting, actually.
In modern language. So David, again, just what's the basic idea of the double slit experiment?
So you take a source of, well, the particles of any kind, but let it be light, for instance. You shine.
So again, you know, you take a particle of any kind. They're completely different things. Okay, I mean, photons, electrons, atoms, completely different things. Some are charged, some are not charged, some are dipoles. So, I mean, they're all different things, and they're all doing different things when they're moving. So, you know, why, you know, this idea that we're going to make this blanket statement that it's all the same phenomenon when completely different results come out. I mean, they are different, really different. And all they have in common is they create the simplest pattern in the universe. I mean, they all create a pattern. Now, creating a pattern is not anything where you class them all as being the same thing. I mean, it's like saying having 5 digits on your arm, you know, makes us the same as a fish. Well, we're obviously related, but we're not the same.
Shine that light as a narrow beam on a screen. It has 2 gaps in it. And you look at the pattern of light behind the 2 gaps in the screen.
Two slits.
Exactly,
Yep,
yeah. So the
yep.
slits are just literally gaps in a black sheet of paper in principle. The light's going through.
So if they did this with the single slit, if they just started with a single slit and tried to explain why there's a pattern, then they would start getting into trouble, because then they have to explain, well, yeah, no, there's 2 waves, you just don't see them. You know, you just don't understand why there's 2.
If light is a particle, you'd expect one sort of result on the far side of the screen. If light is a wave, you might expect something different as...
So again, where this really crashes as a conversation, I mean, it already starts off wrong, is if light's a particle. So I'll just say it again, that these aren't the 2 choices, okay? That you don't sit there and say light's a wave and do this, and you know, obviously it has a length, obviously it has a width, it has dimension, and then use the alternative and say particle. So this equals this whole thing. You know, like a particle would have both of these qualities, that it would have it'd be a big fat thing. So the light particle, by their definition of photon, would be 2,000 atoms across. Okay, that's what they're arguing, and that it would be 2,000 atoms worth of distance of separation, you know, between. No, that wouldn't make sense, because that would be the frequency would be different photons. So somehow the single photon, okay, somehow has to have built into it its frequency, has to somehow be built into this particle somehow. How can that make sense? So, you know, the fair comparison, right? If you want to make fair to the idea of light being a particle, would be to understand that just like your wave has to have nodes to it, you know, like ons and offs and ons and offs, and that there logically would have to be a certain number of these ons and offs in your wave. Your wave takes time to make a photon. A photon isn't in a single event that happens in one instant of time. Even by your own description of the photon, you know that it's not a single event. It's an event where the electric field goes up, and then the electric field has to go down, then the electric field has to go up, and then it has to go down. It has to do a whole series of things. So you can't say photon is this and then force a particle model to be something completely different. No, the particle representation of this would be that there's particles at a distance, okay, and that, you know, you need a certain number of these little particles, okay, to say, okay, a human being can see this photon, but a frog could see this photon, to use a crude shortcut. And the, you know, what I would point out is the obvious fact is this photon is not perfectly parallel. The little bits aren't, their distance is all the same, but they're not lined up perfectly parallel in their travel. And so the polarization of the photon is this dimension. So earlier he mentioned Einstein's photoelectric effect as one of the experiments that is, you know, adds up to this. And nowhere ever in any annal of physics I know of, any place, any lecture, anything, in describing the photoelectric effect, as a single person, you know, dealt with the fact that the difference, the big difference between, okay, so here I'll draw, you know, I'll draw the light as if you people, what you people think. Okay, so the difference between red light and blue light would be this kind of difference, just a frequency change. But the other thing that actually changes is the polarization. The polarization of the red is twice the blue. So not only are you, you know, sending more of these little humps in a period of time, but you're hitting a surface. You're taking all of those clumps and hitting them on a smaller surface. Isn't that a way of saying, oh yes, I'm multiplying the effect? I'm making this thing more intense because I've narrowed its polarization. It's going to, whatever this is going to affect a smaller number of atoms, half as many atoms as the red light. The red light's going to affect this pile of atoms. The blue light's going to affect just this tiny group of atoms. So if we have a simple argument to state for what creates an electron being ejected from an atom, you can understand pretty easily that, well, if the rule is you have to hit it twice, okay, within a certain amount of time, that means higher frequency light is more likely to cause the effect because you're going to hit the same electron twice in a period of time. So if that's the simple rule that creates this effect, well, obviously, if you're sending the energy to a smaller number of atoms, you're more likely to hit the same electron twice. So, I mean, it all fits, but that explanation will never be even talked to. It's never even been mentioned until I mentioned it, right? It's mentioned nowhere else that I know of, anywhere, where anyone talks about the fact that it's not just about the higher frequency. It's about the narrower polarization. That's what makes blue light more invasive, is that it's twice as powerful, maybe even more than twice, right? If you think about polarization going in all directions, you could understand that the circumference, that we're back to the R squared rule, and that half the amount of polarization would be 4 times the amount of space or area you're hitting if you assume the light is polarized in all directions. So it's 4 times more intense in terms of the number of atoms it interacts with. it interacts with the same atoms 4 times as much by doubling the frequency. Ever talked about? No. Ever considered? No. They just jumped to a conclusion, all went that way, and never gave any consideration to any reasonable conversation about reasonable alternative models.
The light coming through one part of the slit interferes with the light going through the other part of the slit. And with
So again, interferes in some magical way for which they won't draw, they won't explain, they won't be able to make any sense of, because it interferes in a way where it pushes essentially the energy, to some other location. So it's not really destructive interference, because in the end, you end up with more energy where the light does end up going.
the thing about quantum two-state experiment is that it seems in various ways to be doing both of those things at the same time.
Good. So, Brigitte,
Okay, so it's doing the same thing at the same time. So that's a pretty poor explanation. Didn't get into the single photon encounters the 2 slits and somehow interferes with itself. That's the real story. Blah, blah, blah.
you can just take...
Well, the real story ends up being also the fact that they say there's a location that light hits from one of the openings. And then there's a location where light hits with the other opening. And it somehow, when both of them are opening, light doesn't hit that location from neither. Somehow the light goes away. And they don't have any experiment that proves that.
us through a particle experiment to build up our intuition. So let's say we carried out the experiment that David described, but we don't start with photons or electrons, we start with bullets or something. So I think we have a little animation that you could take us through. So what would we expect to happen in this experiment?
We have the source of the...
So it almost looks like the Dr. Quantum video. That's how bad this is. It's the same kind of silly description of the concept. So again, it's shooting single particles. Like we know, the photon can't be a single... It's not a single thing. Even by wave theory, you know it's not this. If I draw that and I say that's a photon, none of the physicists will say you did quite enough. So if I just do this one node, right, I just go there, that's a photon, right there, okay, photon. They'd say no, that can't be right. So they know that a photon isn't some ball, okay? They know it is a clump and a clump and a clump. There has to be clumps to it. There has to be pieces to it. So this is a string going through. This is something more. It has a length. It isn't just this. Now obviously I'm arguing it sort of is, in the sense that the clumps are inside that lump, and every single ball will go in a different direction. And all you're really going to do is say how many of those things, when they arrive, you're going to take a bunch of these things that were in order going in. They were all in order. You're going to send them in different directions. But the truth is when they hit this surface, they're going to hit this surface in phase in some locations. And when they hit them in phase, they're going to remake the photon. So the photon gets destroyed going through the obstacle, in the sense that bits of it are sent in different directions. But the truth is you're going to collect them all here. And a bunch of the ones you collect will end up turning back into photons, in the sense they'll get their frequency back.
The pellets here in front, and it's spitting out the pellets, and some of them go through the holes, and the ones that go through the hole, they sort of travel rectilinear, straight ahead, as we might expect from our classical intuition. And we get 2 bands at the back, indicating the pellets that went through the right slit, on the right, and the left band is the pellets...
So again, even if you did these physical experiments, that's not what you're going to get, because a bunch of them will barely hit the surface and get deflected, and there will be some scattering going on. And so again, if you understand that what you're scattering, the thing that really makes it is its frequency, and that when you scatter them, you can take something that went a longer path and something that took a shorter path, and they'll end up being in the right phase or frequency, even though, because they got to the interference, they got to the obstacle course at a different time, but they ended up getting at their location, the final product, at the same time.
went through the left slit.
Now, if I was, that's completely intuitive, right? So this is the stuff that our forebears would have known, even on the spin.
All right, so Newton had already done these experiments, so let's argue. So they always want to go back to like 2,000 years ago to make their comparison, rather than just go back to Newton and the fact that he had already discovered that this happens on any surface. This is what surfaces do to photons. Right? That's all you need is a one surface. The one surface experiment does work. It does screw up photons. So this isn't about slits and splitting in two and, you know, wave interference. It's about surfaces.
Right. Now, if we took the size of the pellets and we dialed them down to a very small size, before going to your quantum intuition that you have, what would you expect naively to happen if you simply dial down the size? Would you?
So let's understand that this is the other part where I'm just saying their physics is so superficial and trivial in terms of dealing with any of these things. So even if you wanted to argue that all the things we call particle, like they don't believe in particle physics, they believe in wave physics, and so these are all some sort of wavicle, you could understand that they definitely have a size, a proportion. So you could say, okay, the electron is this big, okay, this is the electron. Well, we know that the stuff that's actually making the photon, like these little tiny things, the quanta, is very small compared to the electron. But the truth is that the thing we call a photon is very, very big compared to the electron. So, you know, this is way off. This is 1,000,000 times bigger. You know, 1,000,000, might be 1,000,000,000, but let's just, you know, who needs more preposterous numbers? I mean, this is 1,000,000 times bigger than this thing, the photon itself. The quanta inside the photon is 1,000,000 times smaller, okay, than the electron. Maybe. I mean, 10,000, who cares? But some kind of number in terms of its the space it occupies, okay, the space it occupies. So, you know, this they never did. They never created any kind of proportional model. They never drew one of these things and said, what am I really talking about when I talk about these experiments? When I talk about a tiny little slit, what am I talking about in terms of the polarization of the light? You know, if this is the light and this is the slit, well, then I know some of this isn't getting through the slit. Some of this isn't getting through. You can figure that right out without much thinking. You know, doesn't take much.
Expect there to be anything different if you were. This is a leading question, by the way. So just follow me here. The answer is, would you expect anything different? Would you expect anything different? No, not at all. Good. So there we.
Naively not.
Naively not. Exactly right. So here's what you would naively expect would happen. Again, you got the particles going through the two slits. So Mark, tell us what actually does happen. Not that I don't think Brigitte could, just to give us all a little airtime.
So of course it's kind of wild. The place where you would least expect to see something on that screen is exactly behind that big barrier that's in the middle.
Yep.
And somehow, when you actually do the experiment, you see that actually that's where most of the particles end up. So it's always exactly the opposite.
All right, so they completely ignore the photon experiment, you know, and are playing whatever they're pretending they did this electron experiment where they put an electron through a slit that's, you know, tiny enough to break electrons, so to speak, to be a small slit from the electron's perspective, which we can't make. An electron is tiny compared to an atom. We can't make a slit small enough to confine an electron. So that wasn't happening. But anyway, so we know that this isn't the truth anymore. This is nonsense. I mean, the double slit pattern is two patterns. That's what you have to explain. Two patterns. You can't just pretend the double slit isn't fundamentally different. And the difference is overt and right in your face. It sits there and looks right at you and says there's a huge difference. So why are they pretending this is about fringes when this is about a pattern that starts and then stops and then starts again and then stops. That's the real double slit experiment. So this is all just kind of crap to sit there and say all the experiments are doing the same thing. They don't all do the same thing. And they're doing something different for different reasons. There's reasons why electrons do something. They're charged. You know, not complicated.
And then you get this weird pattern with other bands going out, and so you initially would stare at it and shake your head and wonder what you'd actually.
So we'll analyze what that means in just a moment. But you know, we often, I don't know, probably almost everyone in this audience has seen a still image or an animation like this in discussion of quantum mechanics.
Right, on cartoon videos, on videos that are agenda videos like Dr. Quantum, where they're trying to prove that consciousness is controlling the universe because they have a religious purpose. So you don't expect it from scientists. Are supposed to be better than that, and obviously they're not.
And I thought it'd be kind of nice to show that this actually happens. It's not just animation that an artist does. So we're going to actually do the double slit experiment for real right now.
So this is hilarious, just because he's going to do it in a way where you can't see anything. Again, so another experiment where they don't show you anything, demonstrate. I mean, here, the double slit is so easy. You could just shine a laser through something onto the ceiling and show the pattern. Yeah, it wouldn't be a real pretty pattern, but it would show the pattern. There's a fly in here, quite unusual.
And to do that, I'm going to invite a friend of mine from Princeton University, Omalon. Can you wheel out, if you would, the double slit experiment? All right, so what we have here is a laser on this far side. So this is our source. So actually, we're doing this in some sense opposite to the orientation that we saw in the animation.
So this is so silly in the sense that they have this all contained in a bunch of electronics. So they're not gonna shine anything anywhere where you can see it. They're not gonna show you the experiment at all. They're just gonna show you what their detectors say the truth is.
And we're going to fire this laser, which is photons, in essence. And the photons are going to go through a barrier that has 2 openings in it. It's harder to see that, of course, mechanically, but trust me, there's a barrier with 2 openings. And we're going to take a look at the data that falls on a detector screen, which is...
So this is what I mean by, this is such a quote mine of the evidence, right? This is so unfair to the truth, to the real experiment. I mean, I guess I should have put the dopey image up of the comparison between the single slit and the double slit. But obviously we know the single slit with a certain size opening will do something like this. And we know the double slit will do something like this, right? This is the pattern you have to explain. This, with these breaks in it, this is the pattern you have to explain. That's the double slit pattern in photons. Okay? And it seems quite obvious that it's made out of 2 patterns. It's made out of this envelope pattern plus some new pattern that makes these little dots. And as I've pointed out, the math is relatively simple. That these 2 vectors, okay, will give you the tiny frequencies because lots of wavelengths fit in here. That'll give you the little dots. This distance will give you the big envelope. So it creates very few wavelengths in here. Few wavelengths, big things. Big distance, lots of wavelengths, lots of little dots. And it just has to do with putting the whole experiment on a curve, and you can understand there's only so many angles that add up to a wavelength distance difference. That's all there are. And they're all equal distant on that curve. And so that's the truth of it. And so see how far this is from dealing with any of this truth. So they're saying they're proving it with this analysis of the evidence, and this is what they present as the evidence.
The modern age is a more complicated and somewhat finicky piece of equipment. So we're all sitting here on spilkas. If you speak any Yiddish, you know exactly what I'm talking about right there. But hopefully this will work out. So Oman, let's why don't we just actually see ambient noise? Can we see a little bit of that first? So can we switch over to the input to the screen? All right. So this is the output for that device, and with luck, we'll see a little bit of noise. And without.
So again, they're not just shining it on a target. They're not displaying it. They're collecting it. And even that is kind of funny, right? Even if you're going to use diodes or something, why would you put them flat when you know they'll collect distortion, right? So again, I don't have to keep reiterating points, but you can understand that if I was to project this, I'll project it at an honest size here, but if I try to project this one over here, it'll end up being incredibly distorted. I'll make the length of it different. So something that should be this size will look this size. And then it'll get bigger and bigger and bigger on a flat screen. So I'm not really looking at the actual thing being created because I've changed the projection distance.
We won't see a little bit of noise. Are you able to get that to go here? All right. Yeah. So
They have two versions of this video, so I'm playing the version where they didn't edit it. So, because I was just curious. So I saw the version that was edited. So apparently they had some glitches in getting this to work.
we've lost optical alignment. But, you know, thankfully, we did a version of this just 20 minutes ago, which is why you guys were all waiting out in the hallway, and it worked perfectly. And we did actually film that one because we were, like, had some forethought. So can we see? Good. So this is what we had 20 minutes ago. Before, this is now just noise from photons in the room. And now if we actually turn on the laser and allow us to collect all of the photons that land over time, so we can go to the next slide to actually do the double slit experiment, if you would.
So they already seemed to have some alignment, right? That was kind of curious, right? So you're looking at that noise pattern. It seemed to have a little bit of pattern already built into what was supposed to be the noise.
There, they're building up. And there you see what actually happens. So this is a result of this very device here just 20 minutes ago. And you see it. We have a
Okay, so what do they show? They show, so obviously there's only 4 nodes in there, so the slits are very small inside the envelope, right? So if you want to have more bars in that center maxima, you have to have the slits wider, you know, substantially wider than the middle impediment. The middle impediment's telling you how much space you have to fill bars with. So either the middle impediment was very large, or no, very small, or the slits were, well, you know, it's no point in getting into those details. But obviously it's not the double slit pattern, right? It's a terrible representation of the double slit pattern to say, let's only look at this part here, right? So we'll call this the double slit pattern. That's it. Just this one little piece here. We'll ignore this and ignore this by just closing our focus. And that's all they did here. They know this stuff is out here. I'm supposed to believe they didn't know it's there. Yeah, come on. Maybe it's true. Maybe they're that clueless. Maybe they've given that little thought to why they believe what they believe. You know, that little examination of their Bible.
You can see on the very far left, we see some of the photons are landing. Then we get a dark region in between, then a bright, a dark, a bright, a dark, a bright, a dark, and a bright, and a dark, even though
there's 4 on there. So, you know, doesn't exactly very convincing. And again, they should already know that what that is a limited number in 180 degrees. The 180 degrees will have a limited number of those spots, and that's all there will be. There won't be light, dark, light, light, blah, 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 on and on forever. No, there's a limited number in the 180 degree arc, and that should be something they automatically concede. That all they're doing is widening the angle or narrowing the angles, how many angles of wavelength difference there are, and that's it. That's all there is, and they're all proportional. And if you view them on the proper screen, you'd see they're all proportional.
device over here really is a barrier that has only 2 slits in it. So the animation that we showed you actually does hold true in real experiments, and that then forces us to come to grips with it, to try to understand what in the heck is actually...
All right, so come to grips with a completely edited experimental result, right? I mean, a completely... Let's squint our eyes and, you know, narrow our view so we only see the part we want to analyze, we're interested in, because that's the part we want to prove, but we'll not prove the whole thing. We'll not explain the entire experiment. What we'll say doesn't have to be consistent with what actually happens. It only has to be consistent with what we're showing. That's the huge cheat
going on. So it's a pretty piece of equipment for us to have at least seen out here, and with luck, maybe backstage you can get this thing to work, and if so, maybe we can then bring it out into the hallway post the program and people can actually see how it works in real time. Okay, so thank you all, Milan. Okay, so there we have it. We have this situation in which we expect to get 2 bands and we got more. What does that tell us? Where do we go from there, Gerard?
So we don't have any expectations since Newton. Newton already did all these. He did the single hair experiment. He did the single slit experiment. He did the inside and the outside surfaces. He got the pattern. This has been known for a long time that this is what light does. And so there wasn't any big news in 1910 or something that, oh, well, there's this double slit phenomenon. No, that never happened. This is just them rediscovering something that was already discovered and then claiming something new. They can make up a new theory. And it took them, like, even from the Young experiment, which again doesn't explain the real double slit experiment. It has no hope. The two-wave theory doesn't do this complex, more complex pattern. Doesn't do it. Can't do it. There's no mechanism. There's no way to make two waves interfering with each other create that pattern.
Well, as I said before, the question about quantum mechanics, is it real or is it just a tool?
So this guy's likable, because yeah, he's basically saying this is all math bullshit, and we're, you know, maybe we're not getting the variables right. So give this guy some credit.
To my mind, when I was a graduate student, many of my fellow students were doing condensed matter physics, and they were discussing a very interesting model called the Ising model. And the Ising model can easily explain. Imagine a checkerboard, but now a very large checkerboard, very many square fields. And on an ordinary checkerboard, there are black fields and white fields, and they are interchanged. Every black field is bordering to a white field. Now consider a very large checkerboard and consider black and white fields, but in a more arbitrary way they're called black and white. So the only condition I want to have an equal number of black fields and white fields, and then I have an extra constraint saying the number of sides where a black field borders to a white field is also fixed. So now the question is, given the number of black fields bordering to white fields, and given that the number of black fields is equal to white fields, how many ways can you color this checkerboard? And that is physically a very interesting question, because some materials behave that way, and their properties depend on the answer to this question. And it turns out that this is a very difficult problem. So I asked the people, how do you do that? When I tried to calculate it, I was mystified. I couldn't do it. And then I said, yes, there's a paper by a brilliant mathematical physicist called Lars Onzager. He was a Norwegian physicist who went to the States later. And
see, this part doesn't work, right? I mean, without an illustration, you're like, what are you talking about? What are you trying to do? I don't know what you're talking about.
He actually solved the problem. I asked, but how? Because he said, it's difficult to explain. You read the paper by Onzager and his student, Boria Kaufman. Onzager himself couldn't write papers. He was a brilliant physicist, but could not write papers. But his student did. It was a brilliant paper. It was something I'd never seen before.
So they edited this guy out. Because, yeah, what the hell are you talking about?
Paper solved the model, but it was using quantum mechanics to solve it. Now, here you have a problem which is totally classical. The question is a question for which you don't have to know any quantum mechanics to ask the question. You don't need any quantum mechanics to see what the answer tells you. The answer gives you a number. But how did Onzager compute that number? He used quantum mechanics. He used, as if the checkerboard was describing a quantum particle. That quantum particle was doing the trick. It gave him the answer.
Did that convince you of the power of these ideas?
So, quantum mechanics is mathematically an extremely powerful procedure.
Alright, so I would argue that quantum mechanics is just statistics. And obviously statistics can tell you a lot. You know, when you figure out probabilities and do all this stuff, you can figure out that you get to a certain age and you can say, hey, there's a 5% chance I'll be dead next year. You know, so yeah, it can tell you stuff, analyzing statistics, but that's all that is. That's all quantum mechanics is really, is just statistics. It's just mathematics to make statistics understandable.
In fact, in other branches of physics,
but I want everybody here to understand the mathematical structure before we get there. So, so hold that thought for just half a second. So yes, it's absolutely a powerful structure, but let's just go step through it a little bit. So just to finish the double slit story, once we have these multiple bands, what do we do with that idea? And presumably you're going to tell me it takes us to the concept of...
Yeah, so like you were saying, sometimes there are existing tools that you can pick up that you don't think would be relevant to this problem that you're working on, but then you notice a similarity, and so that's what kind of happens here, that there's an existing bit of mathematics that comes up with exactly that same pattern, but it has nothing...
No, there really isn't, so that's just horseshit. Sorry. I mean, it's the simplest pattern in the universe, so obviously there's lots of ways to get there mathematically, so that's just nonsense. The mathematics has you have to put all the information into the mathematics. So if you miss some variable, then you'll miss the output. Now, obviously, they've missed the output altogether, so what they're trying to describe isn't the real experiment. But clearly, the idea that you could understand that there's a path length difference if I'm going to one single point anywhere on an arc, that if 2 points are in 2 different places, the 2 paths will be a different length. That has to go into the math, and that's really already told you the answer to the question. You can draw it. You can do it with a piece of string. You know, you can understand that this arced line is a bunch of vectors.
nothing to do with particles. It's the mathematics that you use to describe waves, water waves, or other kinds of waves.
Yeah, so can we see the animation that has a single, so this is a warm-up to the problem where we have water going through a single opening. Just tell us what we see happening.
Right, well, and what we see is a nice consistent pattern, and we don't see any interference because there's no way for it to interfere with itself. So again, the water example is not a very good example because it sort of proves that this is something else, because the single slit in light doesn't do this.
Happening here.
That's right. So you've got sort of a water wave, a wavefront coming along, and then just that slit acts as a bit of a source for this rippling wave going out in a circular pattern. And you see it's most wavy at the place behind the slits of the wall. That's indicated by the brightness there.
Yeah, and then if we go on to a more relevant version for the actual double slit experiment.
So then they just contrived this, and again, this is the double slit. So again, the double slit is not this easy to see. We go on, off, and here they are stretching the sides because again they're banging it against. They drew a round surface almost. You can almost see there's an arc to this. But no, they're casting it on a flat surface, which is going to distort the pattern. You have to see the pattern from the same distance all the way around to see the pattern for what it actually is.
Yeah, so now we've got that same wavefront, but now there's two slits, and it's like there's two.
I mean, the distortion is obvious. You can understand it if you kept making movie screens wider and wider and wider, and you didn't bend them at all. That people on one end of the screen would be really fat, and people, I mean, there'd be terrible distortions.
Different sources of waves, like if you threw two different pebbles in the pond at the same time. And then what happens is that they're both...
So again, we know that this simple on-off pattern, right, they didn't even space them even close to evenly, But anyway, we know that's the single slit style pattern. I mean, the single slit does this huge giant thing in the middle, which is, still debatable as to what the cause of that is. I mean, clearly they're not showing the double slit pattern. They're showing the single slit pattern. So this is just all, it's so bad that, any fair cop here, right? I'm just saying, if you're a fair scientist, you have to admit, yes, this is a terrible perversion of the reality. They're not showing you the truth. This comes down to being a lie, right? I mean, it's so far from the truth. It has to be called a lie, right? I mean, we know the single slit makes the simple pattern, and the double slit makes the double pattern, the two patterns built into one. And there's no indication of that at all here, and that's so fundamental to the distinction between the two patterns. So again, anyone who wants to argue that this is real credible physics, and this is good physics, and they've really tied up all the loose ends, and everything's clean, and it's the most what do they call it? the most accurate mathematics in the history of mankind or something. Well, yeah, if you pretend the results can be anything, you just draw anything as after the equal sign. If you can just make up what the equal sign's supposed to be, if you can make up the reality and pretend that this fake image of what happens is the real image of what happens, oh yeah, then it's very reliable. But if you have to deal with actual reality, it ain't so reliable.
You're both creating waviness, but some places on the screen, the wave from one is doing this, and the wave from the other is doing this, and they kind of cancel out. But right there in the middle, what's happening is that the wave from the one slit is going up right when the wave from the other slit is going up, and then they do this, and you get a big...
Right, so it has really nothing to do with what photons do, right? If we saw the pattern, it was blinking, right? It blinked on and off, on and off, on and off, on and off. Well, and they were out of sequence. Okay, so the little spot next to it is going dark when this one goes light, and then this one goes light, and then this one goes dark. Now, if that was happening, okay, all this wavy crap might make some kind of sense. That's not what's happening.
Wave, and that's the bright part. But if you work out the mathematics, then the places that have the big waves are exactly these bright ones, and that's just like we saw in the double slit, right, for the particles.
Right. So as Gerard was saying, as Mark is saying, we now have a strange confluence of two things. The data that comes out of the double slit experiment.
So again, they say data, they use this word like we can depend on them to give us the truth, the real data, the facts, what actually was produced by the experiment. And then they'll talk about, like, we can move to the Stern-Gerlach experiment, and they'll say they've discovered this notion of spin, and now they can call they can give every particle, everything in the universe, this quantum property of spin, when the experiment couldn't possibly produce that kind of there's no rational way to extrapolate this function, okay, based on the simplicity of the experiment. The experiment can't tell you all that. It's an experiment on silver atoms, and they're telling me what an electron is doing. It just doesn't make any sense. So we can't depend on them. When they say the word data, it doesn't mean anything, because it's all quote mine data.
When done with particles, and something that seems to have nothing to do with it, where we just have waves going through a barrier with two openings. So the conclusion then is that there's some weird connection between particles and waves. That's where that connection comes from. And
so anyway, I don't know how he connected particles to this nonsense. So again, there's no connection, there's no duality, there's no wave-particle duality. The truth is that all the experiments, if you really analyze them, photons seem to be obeying straight line mechanics. It's all vectors. All of Maxwell's math is straight line vectors. All these curves are completely superfluous to understanding the real mechanism. And I would argue, yeah, if you really look at the evidence, it's particles, it's clumps moving in straight lines.
And let's push that further.
Yeah,
So,
I mean, let's just drive home how weird it should be that there is any kind of connection
Yes.
here. So imagine I do the two-slit experiment. I cover up one of the slits. The effect completely goes away. I get a bit of spreading out of the particles, but I don't get that interference. I don't get those bands.
much as we
All right, so we just said that, right? We know the bands are there, okay, and the feature that's going to change is that we're going to get much smaller bands, you know, bars. So we'll have bands, and then we'll have much smaller ones inside the envelope of those larger bands. But we know single slits create pattern, lots of pattern. The wider the slit, the more the pattern, lots of it.
saw with water going through a
Exactly,
single.
yeah, exactly. Much as you see with water going through the single slit, and much as you see in your classical intuition about particles. If I cover up the other slit, exactly the same result. It's only if I have both slits open at the same time the effect happens. So it seems to be for all the worlds, if somehow something's going through the first slit, and something else is going through the other slit, and between them they're interacting to create this strange effect.
Right, so this is all the hidden variable thing too, see? So, I mean, all this goes to the whole Bell inequality and the fact that they eliminated the possibility of the variable being from a certain point, but they didn't eliminate the possibility that the variable started with the origin. And so as soon as you understand that a photon is not a clump in time, that a photon has to happen over a period of time, so you have to give it a length. It takes time for the photon to start and then for the photon to finish. Okay, it's not something that happens as one event or one instant in time. And once you have that as the variable, it's perfectly understandable. It doesn't violate any Bell inequality.
And that's why it matters so much that I can do this experiment with one particle at a time. If this was just a mass of light going through, no surprise, some light's going through the left slit, some light's going through the right slit, the left-hand light, the right-hand light interferes. But
No, it still does. That still doesn't make any sense because I can't make light interfere. I can't bang a photon into a photon in any other way except to create a slit. There's got to be a reason why I can't make it happen anywhere else in the universe.
I can set this stuff up so only one photon goes through every hour and a half. I still see the effect. It doesn't go down in the slightest.
Yeah, can we see that? We think
So that's another one of the key experiments. So they've told you that, but this whole idea of making single photons is a tricky business. So I've explained this before, but it's worth explaining that if you do analyze all of these experiments that claim to be producing single photons, they all contain this fundamental flaw. They'll create a source of photons, okay, with the experiment in place. And then they'll say, they'll measure how many photons they're getting in their, as a pattern, they're getting something showing up at this other side. And then they'll say, I'm sending single photons. But what they really have to do is send real single photons with no experiment, nothing in the way. And then just have a plain target and send your single photons to really know that these photons are so irregular that there's no possibility that you're getting two of them going through at the same time. So if they did the experiment correctly, that is, they first did a control where they say, okay, I'm getting photons, they're showing up here. I've shot them here, I'm getting them here, and I'm getting them at such a slow rate, 1 per second, or whatever the number would be, that I know 2 of them can't go through the slit at the same time. Then you put the slit in, and what you'll find is this. Okay, I predict this is what you'll find. Only the photon that isn't broken by the system will make it here, and you won't get anything anywhere else, because you really have to have the 2 sources. The 2 sources are critical to remaking the pattern. The pattern is made out of piece from this surface and a piece from this surface, combining, okay, a half from this surface, a half from this surface. Now you have a whole one. Okay, so without that mechanism, without a photon, more than one photon hitting, you have no hope of making the pattern. And if they did that experiment correctly, which, like I said, I've seen, there's no example of it done correctly. They always say how many photons are going through with the experiment in the path. You can't do it that way.
Have the double slit animation with 1 particle at a time. If you guys can bring that up, it'll just amplify what David described.
So, and then you might be thinking, well, maybe each individual particle breaks in half, and half the particle goes through one slit, and half the particle goes through the other slit. But again, then you think you could look, then you think you'd be seeing half-strength detections.
Yep.
But that's not what you see. Whenever you look, each time you send the particle through, if you look where it is, you see the particle in one place only.
All right, so you could do this again with waves. You could understand that even if I sent these things as waves, you could understand the waves are really big, polarization, that pieces of those waves get broken, and you end up with a piece of the wave going here, and a piece of the wave going there, and a piece of the wave going there. What's the difference in a wave theory? So even if I conceded to wave theory, there would be no reason for me not to understand that the photon is a continuous thing, that it can have variable length, that a frog does see photons we don't see for that reason alone. Okay, it's not the polarization of the light that makes a difference or anything else. No, the thing that makes the difference is how much energy at a frequency. And the frog can see photons that are smaller than the ones we see. And we can make a photo detector that sees even smaller ones. And I would argue that ultimately, if you turn that, I mean, I really should invest the $600 in getting one of these photo multipliers. But they all run on, weird voltages, and it's just sort of they should make a new version, a modern version of the photo detector, the photo multiplier. But the idea is that a photo multiplier, you can just turn up the settings, you just turn it up to be more sensitive. And so, yes, first you can set it up so it only sees photons that have 6 units in it, and then you can 5, 4, 3, and if you start making it really sensitive, even if I put it in a big black box, it still starts detecting photons all the time. It goes beep, 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 photon, photon, photon. This, so that's the real background radiation that's there all the time, is the little quanta. So if I turn it all the way up to its highest sensitivity, maybe I can detect gravity. And I end up with a gravity detector. Because it'll pick up just one node of the wave. Just one little node of the wave will be detectable. But again, this is totally ignored. The idea that this thing has to have a length is just totally ignored by physics. It's not even a conversation. Nothing. Never included as part of the conversation is a description of what a photon actually has to look like in the space it's occupying. That it has to have a length. We know it has a polarization, a height, and we know it doesn't have any width. They never deal with these truths.
So trying to reconcile those two accounts of what's going on makes your mind hurt.
Yeah, exactly. So we're forced into David's.
Yeah, I will concede that when you first face the problem, you sit there and you try to figure it out, and it isn't until you get this like I said, you just have to do this simple process, right? I remember doing this years ago. There was something, okay, where the conversation came about where we talked about arcing the screen, and it was like, yeah, that makes total sense. That's how you have to view it. What the hell is all this vibration coming from? Anyway, that's the way you have to view it, to be right. But there was no acknowledgement. Oh no, but it's fundamental to understanding the mechanics that there's a finite number of these little things happening, and so I missed something so obvious. But that's just the procedure, right? The first step is to understand you view it on an arc screen. Well, then you got rid of all the infinities. We know there's no infinite number of little bars. There's a finite number of them. There's a finite number of wavelength differences. And that's it. And it really just has to do with how far apart the 2 point sources are. The further away the point sources are, the more wavelength differences I can make in the angles. And so once you figure that stuff out, it just makes the whole thing so much easier to understand. But yeah, you can waste 10 years thinking about it on a stupid flat plane, doing it all the wrong ways, and you waste 10 years when you just made one simple stupid mistake that would make it so much easier to understand. So that's the trick to it. But isn't that the trick to physics, is to understand and get it right? And instead they've invented all these wooey, you know, we have 400 new particles, we have you know, plus 400 antiparticles, plus all, you know, and none of it fits anywhere. There's no place to put all these particles inside of an atom. They don't fit anywhere. They can't be doing anything. You know, what, well, anyway.
Saying not just thinking that a large collection of particles behaves like a wave, which maybe not wouldn't be that surprising because water waves are made of H2O molecules, particles, and therefore they're kind of wavy. But each individual particle somehow.
So that would be the analogy. Is like, you know, you understand that water. If you were actually a water molecule, what would you see? You know, and it's just pressure, and the pressure isn't from every water molecule. It's probably just going to be one molecule that bangs into you and pushes you and compresses you, and then you have to go into a space that's compressed, and that's going to force other molecules to go up and down and go in all kinds of directions because the pressure is too high. And so the pressure has to, the water can't be compressed. So because it can't be compressed, you can't get rid of the pressure. The pressure has to go the only direction it can, which is up, making a wave.
As a wave-like quality, and historically people struggle to figure out what wave, what kind of wave, what is it made of, and what does it represent if you have a wave associated with a particle. A wave is spread out of particles at a point. And it was Max Born in the 1920s who came up with the strange idea of what these waves are. So, Birgitta, what are these waves telling us about?
Well, the waves are, what we see is a probability, which is a square of the wave, or square modulus of the wave. But
so here's a wave behind you. So you said probability.
Yes.
In essence.
So again, probability and what? They're not going to talk about any kind of mechanism. They're just going back to the fact that we know there's a statistical outcome. So yes, we all can agree there's a probability there's going to be more photons in the middle than there is over there, and lots of that stuff. But they're not explaining any mechanism. They're not giving you any physical, real dynamic to explain how they can make this wave go through space in a certain silly way. And the wave is 2,000 atoms in size, and yet their argument is this big giant thing, you know, this photon, this big giant thing is going to hit something 1 billion times smaller than this, and just that. It's going to bang into this thing that's 1 billion times smaller than it is, this little electron, and it's going to bounce off of it. They think that's how the interactions take place, when I would argue, obviously, the quanta inside this big thing hits lots of electrons and moves lots of electrons one little bit, and that's how the photon works.
But this is an amplitude. This is an amplitude which will give us a probability. But if we take this amplitude and look anywhere here with some measuring device, we will find.
See, the quanta just interact with the electron. Again, this goes back to the photoelectric effect. I mean, it all fits when you really think about it. Just it all fits. But you know, you're talking about this little tiny thing inside. Again, inside of the photon, and the little bits are little tiny bits, and the electrons are little things. But the little bit is going to hit an electron, one little bit, and the one little bit's going to do something. And there'll be another electron over here, and this little bit will do something. And again, it's just about reconstructing what you had before. So if this event took place sooner, because this electron is closer, you know, you can understand, you know, okay, and then you're just going to reverse their roles, where this photon was the one that was in front and this one was the one behind. This interaction will take place, and you know, you'll reverse their roles, you know, because of their position. Should have said it the other way around. This was number one because it went deeper, and now they just reverse. And so instead of being 1, 2, it'll be, when they come out, it's going to be 2 will be ahead of 1. And so, these simple kind of mathematical tricks and sort of understanding that these are events that are taking place in time and distance, and that you can have something that's twice the distance but 1/2 the time, and so they'll end up being in the same place. So if I change this distance and time thing correctly, I can have both of these things come back at the same time. All kinds of different arrangements can pop out of the arrangement of the electrons. So I just move the electrons into different positions, and that can guarantee that the photon bits, will hit different places, different depths, and, well, whatever. But you're just reconstructing. The quanta has interaction with individual electrons, and all you're getting back is part of them that are now reconstructed into a photon.
And with some distinct probability, after measuring many times, we'll find that there's a definite probability of the particle being there, just as in the double slit. After sending many particles through, we found with a certain probability they would all appear on the left.
So that's another experiment they've never done, is to really calculate how much light actually is being killed by the experiment. So, and it's theoretically doable as an experiment, I believe. So if you could shine light on a surface, and you could recognize how much light would hit an area. So if I just shine light, okay, and make it as parallel as possible, and then I shine it on a surface, I can know, okay, just from the size of this, based on how much it spread, that this is how much light in this much space. So I know how much light is in this space. I know how much light is I should have drawn it more dramatically, like this kind of angle. Okay, so I know when the light hits here, I know how much light is 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 here. I know all those answers. So now let me calculate how much light hit here, calculate how much light is here. Now I'll put the slit in that size. Okay, now I know exactly how much light went through here. And now when I collect the light that's going to be spread more, but I collect all of it covering this whole big surface, how many of the photons were killed? How much of the energy is gone? Now, another thing I pointed out is they could just film the whole thing in infrared. Do the 2-slit experiment and then display the pattern and film it in infrared and see if there's any heat changes. Is there energy going to the dark spots and we're just not seeing it as a photon? Very open question. I mean, that's such a simple experiment. You think somebody would have done that by now, right? I mean, so many people have infrared cameras now. You think somebody with an infrared camera would have taken a picture of the double slit. I mean, maybe there's some reason why the camera won't pick up the difference, but I would argue that the energy is still hitting where the dark spots are. It's just not in a form that we can see as a photon.
All right. So in some sense, vaguely, where the wave is big, there's a high likelihood you're going to find the particle. Where the wave is near zero, there's a very small probability that you're going to find the
can't
particle.
guarantee it. So any one particle could be in a place where the wave is very, very small.
Now these
So it's gotten totally irrelevant in the sense that obviously they know the wave isn't some sort of variable probability. It's going in a precise cycle. And that the cycle means there's the difference between the electric field going positive and then the electric field going negative is part of their own argument. So it has very explicit things that are traveling through space, and they've now made it ambiguous into some probability that it's up or probability that it's down. No, there's no probability. It has to be up, and then it has to go down. Those are the rules. So we know there's no variable. It can't go up and then stay up for a longer period of time and then go down at some random time. We know that's a consistent argument. It has to go from up to down at a precise interval in time. So we know that path is solid, that there's no ambiguity about it. And now they're just making it into a probabilistic thing. Well, it's not probabilistic. It's quite deterministic in the sense it had to be in one condition when it got to the slits. It had to be either going up or going down.
are all just pictures. In the 1920s, physicists were able to make this precise. So Schrodinger wrote down an equation. I think we can show you what the equation looks like. Obviously, you don't need to know the math to follow anything that we're talking about here. But you know, Gerard, you wanted to emphasize that.
All right, and this equation is basically saying once you know everything about something, you can predict what's going to be the outcome, and that's all it's really saying. It doesn't demonstrate. This little forky thing here means all knowledge of all aspects of its position and condition. So yeah, the more you know, the more you can predict. Duh. But the equation doesn't answer any questions at all. It's just a statistics. It's a statistical tool. It has absolutely nothing to do. It takes your statistical outcome data and converts it into a simpler formula. But that's it. It doesn't answer the question of why or how or any of that.
There is math behind this because your experience has been that many people miss that point, so feel free to emphasize.
Absolutely. Quantum mechanics, when we talk about it, there's a temptation to keep the discussion very fuzzy. And so I get very many letters by people who have their own ideas about what quantum mechanics is, and they are very good in reproducing fuzzy arguments, but they come without the equations, or the equations are equally fuzzy and meaningless. Whereas the beauty of quantum mechanics is the fundamental mathematical coherence of these equations. You can prove that if this equation describes probabilities exactly as you said before, then actually the equations handle probabilities exactly the way probabilities are supposed to be handled. Except, of course, when two waves reinforce each other, the probabilities become 4 times as big rather than twice as big. But another spots.
Yeah. So they're still having an explanation for how the wave knows to go left or the wave knows to go right. The pressure, let's call it the up. The photons, why they do that. They don't have an explanation. So, but yes, building that into a formula doesn't say anything about a mechanism. And it's again, you're just stuck with you understanding the variables, the real variables. And the real variables are a single photon does not hit a single electron and reflect off or scatter off of the electron. That's missing the variables. You have the variables wrong, you'll draw wrong conclusions. So just like when they use polarization to do all of these entanglement experiments, they're all based on a wrong, the ones that are supposed to violate Bell's inequality. It's only if you understand that the hidden variable is in the fact that you have misdescribed what's going into the experiment, that you've assumed that photons were blocked when they weren't. They were just damaged and that they can be repaired. Once you know that's the hidden variable, there's no Bell inequality.
The waves annihilate the probabilities, and so the probability becomes 0 where the waves are vanishing. So, but all this hangs together in a fantastically beautiful mathematical manner.
Now, math is one thing, experiment is another. So how would you test the theory?
So again, experiment is another, and they don't show the real experiment. So let's just understand, they emphasize the importance of these experiments, and yet they quote mine the experiment. So what's the point? How can it have any integrity when you don't bother to show the actual experiment?
That only gives rise to more probabilities of one outcome or another. How would you go about trying to determine if it's right or it's wrong?
Yeah, so it's like if you gave me a coin and you said, this is a probabilistic thing. You flip it, it's going to be heads half the time and tails half the time. And I want to check that. I don't trust you. I don't know why that would be, but
don't worry, I'm not insulted.
So I just flip the coin, 100,000 times or whatever.
You have a lot of patience.
The more sure I want to be, the more I flip it. So maybe I do it 10 times.
Right. It's not just about how you flip it. It's about how you flip it. Right? I mean, it's about how you flip it, not just how many times you flip it, but you have to guarantee that you put enough variables in, you give it enough energy, that you'll create enough interactions to make it unpredictable, in the sense that you can't predict what the outcome's going to be. And so you're stuck with saying it could be heads or tails, based on the fact that I have synthetically randomized it by making it leave at a different velocity each time and guarantee that I've changed the variables, the amount of stuff it'll hit each time. And with each change in the variables, I'm increasing the likelihood of making either result as an outcome. But we know you can totally regulate that by just changing how much velocity you put into the coin, and then you can make the coin flip 70% heads. You can make the coin flip, any percentage you want by changing the variable. So again, they're trying to tell us that on the quantum level, there's no variables. There's no flipping variables. Why? How do they know there's no flipping variables?
4 and 6, and I'm, maybe I'll flip it 100 times, and then I get 48 heads and 52 tails. So I can basically just repeat the experiment a whole bunch of times, and if I have a very precise prediction from those quantum mechanics equations to tell me...
So again, a very precise prediction that you that you can already predict right from the beginning, because you're just saying I'm going to put something that only has 2 outcomes, and I'm going to create so many variables that there's no way to calculate what outcome you're going to get, just because there's so many variables. There's so many interactions that you're going to have, and inevitably you're going to be stuck with 50-50, because half of the extra variables, the extra variables, will cause a head, and half of the extra variables will cause a tail, and there's no reason that would be unequal. But I'm just saying, there's nothing, the math isn't doing anything very extraordinary, right?
exactly how often I should expect to get one result versus another.
So I think we can give a little schematic. What do we see?
Have a look, right? So we're doing, there's our wave that's describing the state of the particle, the thing without a definite location. Now we're setting that up a whole bunch of times and measuring where the particle is each time, and these x's are showing the results of our measurement.
That's like flipping your coin to get ahead again.
So there's all these possible locations, and what we see is that after a while, the pattern of how often I get one place versus another place is matching up to that expectation given by the blue curve, by this.
Yeah, not necessarily matching very rationally there. So I don't even know what he's comparing. But anyway, so maybe we'll end here and continue this another time. Because I think I made most of the point. So they get into entanglement and all that kind of stuff, and you can just point out how flawed all of those experiments are. And, you know, it's not the neat package they wish to say that we've analyzed all of it, and we've been very careful, and we've been very cautious, and we've done all these experiments, and we've proven it. It's nothing like that. I don't know I don't know what this this vibrating camera thing is. Anyway, we'll have to figure that out. So till the next time and such. And so maybe I'll go back to the Fermilab thing. I mean, there's just always some piece of crap to talk about, which is good, because it does give me the opportunity to point out how, well, that's pretty much just a lie. I mean, you know, what do you call it? What do you call how they describe the double slit experiment? I mean, if it's not a lie, what is it? Because it's just so far from being fair, right? I mean, it's so far from being accurate.